expect you to know in this realm. It's 7.1 in the IB syllabus. And we'll go through a bunch of this today. So let's start with the plum pudding model. Plum pudding model. This is the model that is based on the discovery of the electron. A lot of the nuclear and atomic physics, the stuff that we understand on an atomic and nuclear level, happened in the late 1800s, early 1900s. Prior to this time, chemistry had been really big, and there had been a lot of discoveries about different kinds of elements and creating a periodic table of the elements through chemistry. But really looking at atomic structure hadn't happened. But in the 1890s, J.J. Thomson discovered the electron. And he used a cathode ray tube to do this, and we'll talk more about that later when we get into the quantum component. But he used a device to discover that there are these little tiny things that come out of stuff. Little tiny things. And he called them electrons. He found out that their mass relative to their electric charge relative to their mass was really small. Their mass was really small. And so this was the first solid piece of evidence that maybe there are things that make up an atom, that an atom of gold isn't just gold, but there's something in there, something else in there. And the electron was the first thing to do that. And so if there are these pieces, what does it look like? And the first idea that Thomson came up with is known as the plum pudding model, okay? And when he talks about a plum pudding, I think he thinks of pudding more on an English kind of pudding than we have like Jell-O pudding pops here in America. Yeah. Pudding in Europe or in England, as far as I understand, is more like I don't know what, it's like bread almost. It's like really wet bread. Bread pudding, right. That's kind of how I think of this model, okay? And so the way you visualized an atom, the plum pudding model, is that the atom is this homogeneous sphere that has these little raisins in it, like raisin bread. I think of the plum pudding as more like a raisin bread model. The electrons were randomly dispersed throughout the pudding like raisins in a loaf of raisin bread, okay? That's Thomson's plum pudding model of what an atom looked like. Once the electron was discovered, he had to think, well, then what does an atom look like? And this is what he came up with. Electrons randomly dispersed throughout a homogeneous positively charged sphere. Since he knew the electrons were negatively charged, then he thought the rest of the atom must be positively charged. It was a pretty good model. It made sense. If we knew electrons exist, why not do that? But then this experiment came along that helped to show that the plum pudding model was not, in fact, correct. And here was the experiment. It's a famous experiment. It's known as the gold foil experiment. It was conducted by Ernest Rutherford, as well as Geiger and Marsden helped him out. And here's what he did. In the early 1900s, radioactivity was being discovered, and we'll get into radioactivity a little bit later. But one of the things that happens in radioactive decay is these particles are produced, and one type of particle is known as an alpha particle. And they discovered that certain types of materials, like radium, shot alpha particles at real high speeds. Now, all you need to know right now is that an alpha particle is really small and it's positively charged. Okay, it's basically a helium nucleus, 2 protons and two neutrons together. But they took some radium, shooting off these little positively charged alpha particles near light speed, really fast. He stuck it in a big block of lead with a little opening so that the alpha particles would go one direction. Then they took a really thin piece of gold, really thin, a couple of atoms thick, okay, super thin, thinner than aluminum foil.
How did they cut that? How did they shoot everything straight?
Back to the gold foil experiment. Here's what you need to understand. So Ernest Rutherford takes these alpha particles, shoots them at the gold foil, thin piece of gold foil. Remember, they think atoms are little plum puddings, little pieces of raisin bread in there. They put a viewing screen around it so that if an alpha particle hits the screen, it'll make a little mark. It'll glow. And they just go at it, start shooting at this thing. Almost all of these little alpha particles go and hit the screens right in here, okay? Without any sort of varying course, straight line, maybe slight variation, but very, very little. I'm like, wow, that's interesting. It's going right through. Pretty crazy. They did it for a while. What totally freaked Rutherford out was every once in a while, one of these alpha particles would come back and hit the screen over here. And that was totally unexpected. I think the quote goes, after he did this experiment, he's like, wow, that was so unexpected. It was kind of like if I shot tissue paper with a 17-millimeter gun and the shell came back. Was that in the movie, right? And you talk about that, and the shell came. It was like, wow, that was really unexpected. Well, Why is that so unexpected? Well, if you have this plum pudding model where the atoms are these like homogeneous spheres, then, why are they going through without any deflection? But two, why in the world would they come back? So he's like, something's going on here. Something's wrong. One, since most of them go through undeflected, atoms must mostly be empty space. There must mostly be nothing in there because really these things are just going right through. And two, if there's something in there causing them to bounce back, then there must be something that's really massive and really dense and positively charged. The positive charge must not be distributed evenly throughout. It must be concentrated in a nucleus. Ah, cool. This was the first piece of evidence that there is a nucleus inside of an atom. Okay? And here is what he was imagining happening. Here's the positive alpha particle coming in from the left. If it gets close enough to the positively charged nucleus, the electromagnetic forces will come into play and boom, cause that alpha particle to jump back. That can only happen if it gets close enough. If the atom is uniformly charged and it's as big as they think it is, about 10 to the negative 10th meter or an angstrom, then you can't get this thing close enough to a charge to cause it to deflect back like that when the atom is that big. But if you concentrate that positive charge down to a smaller area, you can actually get much closer, which causes a much stronger electrical force. So that was the first piece of evidence for...
Did he think that they were going to deflect?
So here's kind of the experiment. It was done in 1911. They shot a beam of alpha particles at thin gold foil. Okay, most of them went through without anything happening or deflected at really, really small angles, which basically told them, hey, there's got to be a lot of empty space in there. But every once in a while, some would deflect at very large angles, and this was the big discovery, okay? There must be something really small, really dense, and positively charged in the atom. And it was the first piece of evidence that the atom has this nucleus, which we take for granted today. Okay, so Rutherford did more. Once he figured this out, his next question was, well, cool, if there's a nucleus in there, how big is it? So he did a lot more scattering experiments, shooting alpha particles at foil, measuring angles, and by doing that, he was able to conclude that the nucleus is on the order of 10 to the negative 15th meters. You don't have to worry too much about this, but if you took the number of protons and neutrons in the nucleus, took the cube root of them, and then multiplied by that number, that'd give you roughly the radius of the nucleus. But look, it's on the order of 10 to the negative 15th. Up to that point, they were recognizing that the radius or the diameter of an atom is 10 to the negative 10th. So the nucleus is like 5 orders of magnitude smaller. That's huge. That's on the orders of tens of thousands of times smaller, okay, than the atom itself. It is incredibly small. If you do some calculations, so from these experiments, we developed a new model for the atom, known as the planetary model or the nuclear model. And I think this is the model that most of us have in our heads today. When someone says, imagine an atom, I think this is what you imagine. The idea is this. There is a positively charged nucleus. It contains almost all the mass of the atom. Really, the mass of the nucleus is the mass of the atom. Okay? Almost all of the mass is in there. And the positively charged nucleus is surrounded at enormous distances by the electrons, these tiny little negatively charged things that have almost no mass. The distances we're talking about are hard to imagine. Okay, we're talking about 666,000 times the scale of the solar system. If the sun was the nucleus of the atom, the electrons would be like hundreds of thousands of times. I mean, I don't know. They'd be much farther out than Pluto. Okay, it's hard to even imagine. It's bigger than the solar system. And think about the empty space in the solar system. There's more empty space in an atom. Okay, crazy stuff. This is not a perfect model, by the way. It's a good model, but it's not perfect. It has some issues. It has some problems.
So they developed a better one?
So this is kind of the idea of the Rutherford nuclear planetary model of an atom. Okay, since we've discovered this little nucleus and these electrons orbiting, a lot of people said, oh, hey, that's a lot like the solar system. That makes sense. So we'll put the nucleus at the middle, make it really small and dense. We'll put the electrons orbiting it, kind of like the planets going around the sun, and that's a good model. It seems to work pretty darn well. Awesome. So, but there are some issues. There are some issues, and you need to know what these issues are. First of all, if the electrons are orbiting the nucleus, And they imagine them orbiting like in these nice circulars or maybe even elliptical orbits, kind of like the planets. Well, that's accelerated motion. Remember, centripetal motion is accelerated motion. And one of the things about accelerating a charged particle, like an electron, is it emits electromagnetic waves. The electromagnetic waves that we receive from the sun and from anything come from accelerated electrons. So if the electrons are moving acceleratedly around the atom, they should be emitting radiation. Every atom that we ever see should be emitting radiation. And they don't. That's a problem. And furthermore, if they emit radiation, the electrons should lose energy, conservation of energy, right? If they're giving off radiation, they should lose energy, and therefore they should actually spiral into the nucleus and die. And they calculated how quickly this should happen. It should happen on the order of nanoseconds. Every atom in the universe, if this model is true, the electron should emit radiation, spiral in the nucleus, and die within a matter of billionths of a second, okay? And we know that doesn't happen. That's a problem with our model, okay? Okay? So the electrons should be spiraling into the nucleus. Also, just as you think about it, if they were spiraling into the nucleus, not only should they be giving off radiation, it's kind of cool to think about, but as they spiral in, they'd be accelerating faster and faster and faster. So they should be giving off a rainbow of colors as they spiral in and die. It'd be kind of cool. It would be cool. It doesn't happen. So what we should observe, according to this model, is a spectrum of radiation coming out of atoms. And actually, that doesn't happen. We do get radiation out of atoms, but it's not a full spectrum. We get very specific spectral lines. And we should have, all atoms should be unstable. Electrons should spiral into the nucleus, cause atoms to decay. And some atoms do decay, but most of them don't. Most of them are quite stable, as you are aware, because you are here to think about it. Okay? So one of the things this thing is saying is that atoms should give off a rainbow of colors, a complete spectrum as they decay into nothingness. And this should all happen on the order of nanoseconds. And it doesn't happen. But atoms do give off spectral colors. And this was discovered about the same time in the Kirchhoff-Bunsen experiment. These guys were some chemists that were doing some things. And what they would do is they would take an element. They would take an element, like see this little powder in this little spoon here, and they would burn it. They'd drop it in. They'd drop it into a flame, and they would burn it.
So they were burning one
Okay. And when they burn these elements and they analyze the light, they shone the light through a prism, which divides light into its different wavelengths, because you guys remember that from waves last time because of index of refraction and all that stuff. What they found is that the light coming from an element wasn't a rainbow of colors. Rather, they'd get very specific colored lines. And the more they did this with different elements, they found that every element would give off colors at its own specific wavelength. It was like a fingerprint for each element. Each element had a fingerprint of spectral lines, and it was really cool. They didn't know why, but it was really cool. These guys were actually able, I think when they were doing this experiment, I read somewhere there was a fire all the way across town, and they pulled out their little apparatus, and by looking at the light from the fire across town, they could tell what kind of things were burning. It's like, wow, that's really cool. So, spectral lines, we just talked about it. Emission and absorption spectrum. Now, cool. So there's two different kinds, there's actually three different kinds of spectra that exist. Emission, absorption, and what's called continuous spectra. And I'm going to show you the next slide to explain that. But this little picture here would be an emission spectrum. If you took something and you make it glow, and you analyze its lines, you have these glowing lines, those are emission spectrums. That light is being emitted by that material. Okay? The other possibility is that if I have a glowing solid, or something that's really, really dense, like the sun, when it glows, if I analyze the light, I will actually get a full rainbow of colors. This is called a continuous spectrum. Okay? If I take some gas that's not really dense, let's call it helium, and I heat it up so it's glowing, and I analyze its light, I will get an emission spectrum, or a bright line spectrum. I'll see bright glowing lines that are unique to that gas. If, however, I take continuous light, something that would produce a continuous spectrum, and I shine it through some helium gas that's not glowing, that's just cool, like a nebula out in space, when I analyze that light, I get a continuous spectrum with some lines missing. That's an absorption spectrum, and the lines that are missing are exactly the lines that I would get if I took that same gas and made it glow. So it's like a particular element will either give off light or absorb light at very specific wavelengths that are unique to that element. Okay? So once it was discovered that atoms create spectral lines, there was a lot more research done to find these spectral lines. And three main people, Lyman, Balmer, and Paskin, did research to discover spectral lines, and they did a whole bunch of research. They mapped them out. And this was, I think, the spectral lines that I think hydrogen can give off. And notice there seems to be a pattern. There seems to be a pattern. They didn't know why. They didn't know what it was, but it sure looks like there's a pattern. And if we could figure out this pattern, perhaps we could figure out something about atomic structure, what's going on in the atom. So leave it to this crazy guy named Niels Heinrich David Bohr. Bohr. You probably heard of him before. He did a lot of cool stuff. And Bohr comes along and says, you know what? Let's get a picture of Bohr. Oop, come on. Where is he? There he is. There's Niels.
He looks too young.
Guy was brilliant. He says, you know what? The planetary model that Rutherford has given us, it's pretty darn good. But quantum mechanics was happening simultaneously as all this stuff. Quantum mechanics was being developed. Max Planck, Einstein, all these people were coming up with these ideas of quantum mechanics that we'll talk about later. But he said, you know what? If we're going to have a model of an atom, it should also incorporate this idea of quantum physics that are being developed. And the basic tenet of quantum physics is that certain quantities don't exist at all values. Certain quantities can't exist at all values. They can only exist at specific quantities, thus quantum quantity. So, for example, energy. We think of energy, you can have as much or as little energy as you want, but on the quantum mechanical world, that's not true. You can only have very specific quantities of energy or angular momentum, things like that. And he thought, well, shoot, the atom, if we're looking at atomic structure, the atom should also incorporate this idea of quantum nature. A good analogy to thinking of things in the quantum way is the difference between a ramp and a staircase. Okay? If you're walking up a ramp, you can go any height you want. You can pick whatever height you want. But if you're walking up a staircase, you can only exist on stair 1 or stair 2 or stair 3 or stair 4 and nowhere in between. Okay? That's quantum. That's looking at something in a more quantum way. So what does that have to do with atoms? Well, here's what it has to do with atoms. Bohr was thinking about the spectral lines and quantum mechanics, and he said this. Okay, let's imagine that we have a nucleus and the electrons exist orbiting around the nucleus. But instead of them existing at random places, let's assume they can only exist at very specific locations. They have orbitals, specific energy levels where they can exist. And that has to do a little bit with the mathematics of angular momentum, which I think the movie talked about the other day. But we don't have to worry about that. He basically said, what if angular momentum can only exist at very discrete quantities? He did the math and discovered, hey, then the electrons could only exist at very specific orbitals. And what if, when the electrons either jump up to a higher orbital, they would absorb energy, or if they jump down from higher to lower, they would release energy. Okay, and they would only release or absorb very specific amounts of energy because those orbitals only exist at very specific points. Then we would observe spectral lines. We would observe lines at very specific wavelengths because that would indicate very specific energies. Okay, so he starts thinking about that's what creates the spectral lines, and here's what he decides. He says, you know what? Maybe the electrons don't actually flow from one level to the other. They actually make a quantum leap, a quantum jump. So if an electron exists at this orbital in an excited state, it can decide, well, it probably doesn't decide, it just does this. It can jump down to this lower orbital, and it doesn't exist in between. It actually disappears and reappears or makes some sort of a quantum leap from this orbital to that orbital. And in the process, it gives off a photon of energy, which equates to a very specific spectral line of light. If it jumps from a lower level, notice this is a smaller jump. That's less energy. So it'll give off a photon of light with less energy. Longer wavelength equals less energy. If it's a bigger jump from a higher orbital down, it gives off more energy. But it can only do it at very specific levels, and that's why we don't see a rainbow. That's why we see specific spectral lines. Okay? Why does this happen? He doesn't know. But he says, hey, it works, and the math coincides with the spectral lines we observe. So there must be some truth there, even though I don't know what that truth necessarily is. It appears that this is true. Okay? The Bohr model complied with the observed spectra that they found of hydrogen, and it made predictions of new lines. That was the cool thing. A model is really good if it does two things. If it explains what you observe, but also if it can make predictions that you can verify, then you've got something good going on here. And he did that. He said, hey, I can explain the spectral lines we've observed, but if you use my model, I think you should find a spectral line here. And they went out and looked for it, and they found it. So, wow, that's good. That's a good model. Things are looking good, okay? But it made some assumptions. It made some assumptions. He said basically, one, when the electrons are in their fixed orbital, when they're in a certain orbital, they're not going to give off radiation. Why? He didn't say. He just said, you know what, I'm going to assume that just doesn't happen. We don't see it happen, it must not happen. Two, angular momentum is quantized. It can only exist at very specific quantities. Why? I don't know. It just does. He doesn't explain how the electrons move from one energy level to the next. It's just that they just do. They just jump, and they just do. And it was such a good model. This was such an incredible discovery that he was awarded the Nobel Prize for this idea in 1922. He was only 37 years old at the time. Pretty remarkable. Okay? So now let's go back to those spectral lines that were observed before. And now there's an explanation for it. And he was able to calculate, not only using what he understood about the mathematics of quantum mechanics and things, he was able to calculate that the lowest energy state for hydrogen is actually at negative 13.6 electron volts. The next orbital is at negative 3.4, and the next one is at negative 1.5. Notice that infinity, this is kind of like when we talked about potential energy last year, of gravitational potential energy. We said that your potential energy would be 0 at infinity. Well, on an atomic level, he was doing the same thing, that we have negative potential energy here, and we go out to 0. So here's the lowest ground state, n equals 1. If the electron drops down here, it's going to give off from n equals 2 to n equals 1, it's going to give off a particular photon of light or of energy. If it goes from 3, it'll give off a higher energy photon, because that's a bigger jump in energy. And notice it can do all of these. And I think the ones that are visible, I believe, are in the Balmer series. Somewhere in here are the ones that are actually visible light. These are actually going to be ultraviolet. Those are ultraviolet spectral lines. And these are actually going to be infrared spectral lines, because their energy levels are lower than in the visible spectrum. When we get into the electromagnetic spectrum, we'll talk more about that. Okay? Here's a question that comes up quite frequently. Now, the Bohr model of the atom was a good one, but it wasn't perfect. It wasn't perfect. It doesn't work when you start having more than one electron. Like you get into atoms bigger than hydrogen, it wasn't great. But it sure worked great for hydrogen. So, you know, it didn't explain why some lines were brighter than others, okay? It didn't explain why atoms bond to make molecules. And there really was no experimental evidence for these postulates that he came up with, other than the fact that that's just what seems to be happening, but there's no evidence why that should be true. Why should angular momentum be quantized? But other than it could predict what was observed, bless you, with spectral lines. Okay? Okay, so the next question, this is looking at electrons in the general atom structure. The next question is, does the nucleus then have structure? If there's this nucleus down inside of the atom, does it have some sort of a structure? And it's relatively complicated. Nuclear physics gets kind of crazy. Not totally understood, but we have good ideas. And just to give you an idea why, the nucleus is so small is one thing, and it's so powerful. But basically about 30,000 carbon nuclei would stretch across a single carbon atom. Again, the nucleus is, you know, tens of thousands of times smaller in size than the entire atom itself. By about the 1930s, they started to understand that there are these things called protons and neutrons. The protons were discovered relatively easily. Neutrons were much harder to discover because they aren't charged, right? And so you can't use electric forces to try to detect them. It was a pretty complicated experiment. Constituents of a nucleus, protons and neutrons. We know those are the two things that make up a nucleus. Okay, what's the charge on a proton? Positive, +1. Okay, good. And a neutron?
0.
Neutral. It is neutral. That's the idea of the name, neutron. How about their mass? In general, are they massive or not massive?
Which one?
Protons and neutrons.
Yes.
They're much more massive than electrons. And relative to one another,
Same.
they're about the same. There's a slight difference, but there's about the same. Excellent. So, they are about 2,000 times more massive than electrons. Okay. So again, when we say that almost all of the mass of an atom occurs in the nucleus, that's true. The constituents of the nucleus are 2,000 times more massive than the electrons that are orbiting them. So when we want to know the mass of the atom, we really mostly just deal with the mass of the nucleus, and that helps us. Now think about this for a second. You have this really, really small thing, protons and neutrons globbed in there. What charge are protons again?
+1.
Positive. +1, positive. They're all globbed in there together, they're positive. According to what you learned about electricity last year, what should they want to do? They don't want to be together. Electromagnetically, they want to be away from one another. But they're globbed in there tight. Something's holding them together. There must be some other force. We have a name for it. We call it the strong nuclear force. And the strong nuclear force must be stronger than the electromagnetic force in order for them to stick together. And at very short distances, that is true. The weird thing about the strong nuclear force is as soon as distances get bigger, it gets really weak, really fast. Okay? And then electromagnetism can take over, and then protons can fly apart, and then you get all sorts of things like radioactive decay. Here's some vocab for you. Here you go. You ready? Vocab. Nucleon. Nucleon. Awesome. A nucleon is basically something that makes up the nucleus. So we know that to be protons and neutrons. Protons and neutrons, we call them nucleons. Hey, how many nucleons you got? I got 12. All right, I'm carbon, or whatever. You know what I mean? Okay, so that's what nucleons are. Okay? A nuclide. Nuclide is a word that are all the different kinds of nuclei collectively. So when you look at the periodic table of the elements, all those different elements are a bunch of different nuclides. Okay? Okay? Yeah, crazy word.
They all sound the same.
Atomic number, represented by the letter Z, is the number of protons in the nucleus. Okay? Which basically tells you what that element is. Okay? The number of protons tells you the characteristics of that element. The atomic mass, A is the total number of nucleons in a nucleus. The protons and the neutrons is the atomic mass. What's that? Which leads us to our next vocab word, which is isotope. What the heck is an isotope? Okay. Awesome. Okay. If you have nuclei that have the same number of protons, which means they are the same element, but they have different number of neutrons, those are different isotopes of that element. Okay? For example, carbon. How many protons in carbon? Protons. 6 protons. If you have a nucleus with 6 protons, it's carbon, no matter what. If I have 6 neutrons, I call it carbon-12. But sometimes carbon has 8 protons, and we call it carbon-14. Okay? And we can use that for radioactive dating, all sorts of things. But carbon-14 and carbon-12 are 2 isotopes of carbon. They have the same number of protons, differing number of neutrons. Oh, I got 2 lines. I don't want to. So the terminology we use in physics goes like this. X will be a letter or 2 letters that tells us what the element is. A will be the atomic mass. Z will be the atomic number. For example, carbon, 12, 6. That's kind of how we'd write it when we're doing nuclear physics. A lot of times you can even omit this number, however, because just by writing carbon, I know it has 6 protons. So I could call it carbon-12, or I could call it a different isotope of carbon, carbon-14. Those are still both carbon. They still have 6 protons. They have differing numbers of neutrons. Okay? Hey, look at that. What's that?
Uranium?
Here's the last slide. We can do it. I know we can. I know, but thank you. That's killing me today. How did we discover isotopes? How did we discover? Well, they used this tool called a mass spectrometer. A mass spectrometer was able to discover that you could have certain atoms or certain nuclei of a given material and have different masses. And it's a really cool tool that I'm going to show you a little bit here how it works, and you should understand it. But just so you know that isotopes are atoms with different numbers of neutrons. We just talked about that. They have the same chemical properties. It is the number of protons that determine the chemical properties of a particular element. Okay? So 6 protons makes carbon be carbon. And because of that, the electrons associated with it. But it'll have different mass and different nuclear properties. Different isotopes will have different nuclear properties when we get into nuclear physics. Recognize that chemical properties, things you studied in chemistry, tend to happen because of the electrons. Nuclear properties happen because of what's going on in the nucleus. So when we get into nuclear physics and nuclear bombs and nuclear energy, that's happening on a nuclear level, and it's more powerful. Nuclear bomb. Yeah. Okay. So the mass, when we get down into this one, a common unit for mass is known as the atomic mass unit, AMU, or more abbreviated just U. And the definition of an atomic mass unit, it is defined as the mass that is 1/12 the mass of a neutral carbon-12 atom. That is the definition of what an atomic mass unit is. Using that unit, a proton has just about 1 atomic unit of mass. A neutron has just about 1 atomic unit of mass. An electron has about 1/2000th of an atomic unit of mass. Okay, so it's a common unit that we use, and it's defined as 1/12 the mass of a carbon-12 atom.